Okay, remember that invariably in statistics, we're dealing with samples. And the problem with samples is we've always got, this large population, and we're trying to draw conclusions about the population from a smaller sample. And so there are all kinds of hazards that go along with this that kind of fall under the general heading of sample error or sampling error. So what I want to do in this video is to take a look at first of all, the kind of methodological issues that go along with sampling, and talk about just a few things you should definitely be familiar with in terms of procedure. What is a sampling frame, and the difference between a simple random sample and a stratified sample. And then I also want to get into the statistics of sampling. So even if we do, even if procedurally we go about getting a very good and representative sample, there are still issues that have to do with the fact that our sample is smaller than our population. And so we're going to look at concepts of the standard error of the mean, this theorem, the central limit theorem, that lets us draw some very good conclusions. And then finally, we're going to talk about confidence intervals and how to set those up. As an opening case, let's think about this example. Let's say we've got a machine on the shop floor that creates these bolts, and we're interested in making sure that these bolts, of course, meet certain standards, the production standards. Okay, so there are all kinds of attributes that could be of interest, but let's just say for our test we are measuring length, and there's a certain length that these bolts need to be in order to conform to specifications. So let's say that what we do is, we produce several thousand bolts every single day. We're not going to measure every single one, but we do want to take a sample. So our process here then is to every so often take a sample and then to measure those and to see how close they are, to see if they conform to this length specification. Now, let's say that the way we go about this is we tie it into our daily operating procedure, so that, let's say, after every 1,000 runs, or let's just say 100 runs, we change some kind of filter. Let's say we change an air filter, and taking into consideration the fact that there are all kinds of environmental attributes that might go into making the length of these bolts a random variable. So there are differences in humidity and temperature and pressure, and there's all kinds of factors that could affect it. So let's say after every 100 runs, we're required to change a filter. And then we go ahead and take that opportunity to extract this sample, 1, 2, 3, 4, 5. We take out the first 5 bolts of the next run, and then we measure them, and then we see whether they are the right length. So this is an example of sampling that might be a little bit problematic. And so what's the problem with this? Well, we're tying it into some kind of process that might actually change what we observe. So, what would happen if by changing this filter we reset some things such that the length is fairly well controlled at first, but then as time goes on, the length starts to diverge. And then, so the problem is, by taking those first 5 bolts, rather than spreading it out, we're not really getting a good sample. So we have some sampling error there. And the problem is that it's just not representative. So we need to think a little bit more about how we go about taking our sample. So even before we get into issues of quantitative analysis, we have to think about the procedure that we go through to get these samples. Here's another example that might be, it gives it a more, relevant to social sciences kind of feel. Let's say I was interested in study habits of students here at this university. And let's say, I wanted to, just get a sample of 30 students. And we'll get into why 30 later in this video. Let's say I just take 30 students. And the target variable is, so the random variable is hours per week of study. And the first thing you have to consider is your sampling frame. Okay, so the sampling frame is the mechanism that you use that represents your population. And so this could be, this is like your starting big set. How do you start off with this big set? Could be every phone number in the phone book, or it could be a complete list of all employees, or it could be census records, but you're starting with some kind of sampling frame that you use to select from. You select from that sampling frame to get your sample. Okay, so let's say that I use as my sampling frame BTs at 1 a.m. on a Tuesday. So I stand outside BTs at 1 a.m. on a Tuesday, and I survey students that are coming out about their hours a week of study. Okay, now with this, I'm guessing here that this is probably not a very good representative sample. That if you are, at BTs at 1 a.m. on a Tuesday, this might indicate, certain habits. So there's going to be some bias in that sample. You may not really represent the population of Radford students if you're there. In terms of the hours a week of study. Now, likewise, let's say we're here. I'm not really sure what the hours here at this library are, but let's say you're here, at the library at midnight on a Friday. Okay, so now our sampling frame is this, and we stand outside the library at midnight on a Friday. Now, that probably if you're at the library at midnight on a Friday, this is showing an extraordinary degree of dedication and industriousness. So this is probably also going to be biased on the high side. So once again, we're going to have a biased sample. Okay, so the basic idea here is that we have a sampling frame that we use to go about extracting our sample. And we need to be careful about introducing bias with our procedure for actually getting our sample from a sampling frame. Okay, so there are two kinds of sample that I want to go over. The simple random sample. And with a simple random sample, you're just going to go down your sampling frame. Let's say this is a list of every person in the population, and we just randomly select from it. Just randomly select, randomly select, randomly select. And what's going to happen with a simple random sample is it's going to be what we call a probability sample. Probability sample means that you're going to represent the subjects proportionally to how they occur in the population. So for example, if this sample frame consisted of 25% males and 75% females, if we were to select randomly, our sample, lo and behold, would have 25% males and 75% females. Okay. So that's what we mean by a probability sample. So these, because we're selecting randomly from the sampling frame, we're going to wind up with, the proportions of the original population are retained. Now, in contrast to a simple random sample, we have a stratified sample. Let's say that for whatever reason, if we were taking a sample of Radford students, we don't necessarily want a probability sample. So this will be a non-probability sample. We don't necessarily want exact representation because we have more freshmen than we have seniors. More freshmen than seniors. But we're interested in getting a good solid representation of every class. So instead of getting a simple random sample where we would find our seniors underrepresented, we want to take a stratified sample. That is, we define these strata. So this would be freshman, sophomore, junior, senior. And we just decide, okay, we want to take a certain number from each. Let's just say we want to take, in this case, we want to take 4 from each of these strata. So we'll take 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so we have a simple random sample within each of the strata. Okay, so that's just some basics about sampling that have to do with the procedure that you use to obtain your sample. But I want to talk also about the actual statistics of sampling and some of the things that happen simply due to the fact that subsampling from a population has certain effects on certain measures of interest. And I want to show how this happens through an example. Okay, let's say we wanted to flip a coin, or let's roll a die. Okay, so we're going to roll a die, and we're going to roll it 6 times. Okay, now we don't have to do this physically because we can have Excel do it for us. So I'm going to take several samples of each of which contains 6 rolls of a die. Okay, so you think about this. Now this is a discrete uniform distribution. So there are 6 possible outcomes, and so you would expect that there would be 1 1, 1 2, 1 3, 1 4, 1 5, 1 6 in each sample, roughly. Okay, so it's not always going to be like that. So let's go ahead and just see what happens, and let's create some random samples of die throws. Okay, let's do 1 2 3. So these will be our samples. And I'll go ahead and have Excel continue this pattern across here as far as it'll go. Let's see. So we'll take 12 samples. Okay, and I'll just color that so it'll keep it distinct. Okay, so in each of these samples, I want to roll a die 6 times. So there'd be 1, 2, 3, 4, 5, 6. So we'll go up to row 8. Okay, so how do I get a random integer between 1 and 6? Excel will let us do that with its function rand between 1, 6. Okay, so give me a number, an integer, a random integer between 1 and 6. Okay, and it happened to roll a 1. Okay, so we'll do 1, 2, 3, 4, 5. Okay, and each time the worksheet updates, it does it recalculates everything. So if I were to just roll again, each time I do this, it rolls again, and you see, okay, so it just does a different draw each time. Okay, I'm going to do that. So each of these is a sample. So let's take a look at this first sample then. Let's take the mean of it. Okay, so what would you expect the mean to be. So remember that the expected value of a uniform discrete, and we went over this in an earlier video, is going to be the lower bound plus the upper bound divided by 2. So it turned out, and we knew this from from our previous calculations, that for a die that's 3.5. So we would expect the mean to be theoretically 3.5. Okay, so let's see what the actual mean is. So we'll take the average of these rolls. Let's see, did I have enough rolls here? 1, 2, 3, 4, 5. Oh, I actually want 6, so let's do, there's not really any particular reason, but just so that we'll have 6. Okay. So the mean here, so will be average of these 6 throws. Turned out to be 3. Calculate again, 3.6, 3.3, 3.6. Okay, so let's go ahead and take a bunch more samples and take the means of all those. So I'll just take these rows. Well, let's see, I take these and copy. Okay. I can just select the whole range, but I kind of like to watch it happen. Okay. All right. So there it goes. So now we have 12 different samples of 6 rolls each, and see this now is 4, 4.8, 3.1. Okay. Let's go ahead and take the average of all of those. Now 3.5, that's exactly the expected mean for the expected value for this particular distribution. So let's go across and take the average of all of these, and I'm gonna select these cells and format them as numbers so that I don't have quite so many decimal places to look at. Okay, so interesting thing here. So let's treat all of these as our population then. So we've got 12 samples here from some larger population, but let's say that these are a whole population. And so let's say our population mean, so we'll do population parameter, population mean. Actually, let me put it here, population mean. Okay. Sorry. I actually want to go ahead and use the symbol here just to show you how to do it. If you go to insert and then symbol, you can use the mean here. Remember, we used the Greek. Use the Greek letter for the population parameter. So we'll color these. So we'll make population parameters green here. Okay, so what's our mean? So we'll take the average. So the population average of this whole population is 3.8. Okay. And our standard deviation. Now again, we can use since we're talking about population, we want to use one of these Greek words here, this Greek characters here. So that'll be there. And so we can just do standard deviation of this entire set of numbers here. Okay, so it's like 1.7. Okay. Now, see, each time the worksheet updates, it gets a new draw, and we can see what happens. So this population mean always hovers around 3.5, give or take, and it looks like this standard deviation always hovers around 1.6 or 1.7. Okay, so let's treat those as our population parameters. Once again, I'm going to format some cells here so that I don't have to look at too many decimal places. Okay. Okay. Now notice that from sample to sample, I have a different mean. And this is pretty important. So if you look across this row here, we see, the expected value of this would be 3.5, but because of the randomness inherent in drawing a sample, we've gone, let's see, we've gone as low as 2.17 here and as high as 4.5 here. Okay, so what would be interesting to us over time is, well, let's think about what would be the average of the averages. Okay, so let's do this over here. Okay, so we put population parameters here, and we're going to put in red our sample statistics, right? Format these as red just so we can differentiate. So this is going to be the mean of means. Okay, so this is going to be, we're going to go across all these different sample means and take the mean. Okay, so what is the mean of means, or the grand mean? What's the average of all of these averages? So we'll do average of all of these. Okay, and as you would expect, it is precisely the same as what we saw before. Okay, for the population. And the reason for that is because we have taken every single, we have all of these observations are included in here. But let's just say we only took, say, 8 of these samples, and we'll just chop off these last few. Let's say we never took these. So now these, we still have all of these included in the population, but now we've only drawn 8 samples. Okay, so now we see what happened is we've got a population average that is, a little bit different from the mean of means, or the average of all the sample averages. And let's just watch the behavior of these as we kind of fiddle with it. Okay. Okay, they're never precisely the same. They're always just a little bit off. Okay. Well, so we've taken the mean of the means. Let's see what happens when we take the standard deviation of the means. Okay, we see now we've got 3, 4, 4. It's always around 3 or 4. Well, let's take the standard deviation of those means. Okay, so standard deviation of all of these sample means here. Okay, and we have a number 0.56. Okay, so what is this number? So the standard deviation of means. Let's see what happens when we take this population standard deviation. So we're going to take the population standard deviation, and we're going to divide it by the square root of the sample size. Okay, so we're going to do that population standard deviation, which is here, and then we're going to divide it by the square root of 6, which was our sample size. Okay, so we'll do that. So we'll take this divided by square root of, and our sample size was 6. Okay. Okay, and it's 0.65, but let's, okay. Now notice that this number is fairly close to this number. So the standard deviation of the means turns out to be approximately equal to the population standard deviation divided by the square root of the sample size. And let's just keep doing this. We see that sometimes it's higher, sometimes it's lower. but these numbers appear to have some kind of a relationship. Okay. So what we're seeing happen here is a couple of interesting things. First, that this average of averages here, that if we take a whole bunch of samples and then take the averages of those samples and then average them all together, we wind up having something that is quite close to the population mean. Not exactly, but it's fairly close. And the standard deviation of all those means is going to be approximately equal to the population standard deviation divided by the square root of the sample size. Okay, let's take a look at this slide to hopefully this will make this a little bit more clear. So these things that we saw happen in action are parts of the central limit theorem, which tells us what happens to sampling distributions. Now, so the statistic of interest that we were just taking there was the mean. So we were looking at sampling distributions of the mean. So what this refers to is if you take a bunch of samples and then take those means, this is what this will look like. So this is saying, okay, so the average, okay, so the average of all of those means, so this is what I was calling the mean of means, or the average of averages. It turns out that the average of those averages is going to be approximately equal to the population mean. So if we want to try to get at what our population mean is, if we take a bunch of samples and then take the means of those samples, we're going to get something fairly close. Okay, so this is one part of the central limit theorem. Okay. Now, what it also tells us is that the standard deviation of those sample means, okay, so notice the subscript on both of these. This is the mean of means, and the standard deviation of means is going to be equal to the population standard deviation divided by the square root of the sample size. Okay, n is sample size. Okay, now, so notice a couple of things. So this gives us some kind of measure of how different all of our samples are, right? So if from sample to sample, we have a large amount of variability, then what that tells us is that we can't really trust that our samples adequately represent the population, right? Because if we take a sample and then the next day we take another sample and we have wildly different means, then that tells us that we have a very high degree of variability across samples. And so therefore, we have to be careful about drawing conclusions from a sample, because that sample is not going to be the same as another sample. And so that means that, we don't know which one better represents the population. So this standard deviation of these means has a particular name. This is called the standard error of the mean. Okay, so the standard error of the mean, or SEM for short. So this tells us across samples how much variability are we going to have in our means. Okay, and notice that it depends on two things. This is the amount of variability that we have in our original population, right? So notice that this doesn't have a subscript. This is just the standard deviation of the population standard deviation. So it depends on how much variability. Okay, so the variability across samples is going to increase if you have a lot of variability in your original population. Okay, now second, the variability across samples is going to go down if you have larger sample sizes. Okay, so let's say I were to take, I'm going to use a height example again. If I were to take samples of, let's say, 2 people, and then I were to take their average height, there would be a huge amount of variability from sample to sample. If, however, I were to take samples of 50 people and then average those, you would see that there would be much less variability across those samples. Okay, so the variability across samples increases with the variability in the population and decreases with sample size. Okay, and this particular measure here, this ratio, is called the standard error of the mean. Okay, and the central limit theorem also tells us something else. It tells us that the sampling distribution, that is the distribution across samples of means, is normally distributed even if the original population is not normally distributed. So what the reason that we care about this is because when we get into hypothesis testing, we're going to want to assume a normal. In order to draw a conclusion about a population parameter, we have to assume a normal. But what the central limit theorem lets us do is to make that assumption safely, because even if the original population is not normally distributed, the samples will be normally distributed. Okay. Okay, so that's very abstract. Let's go ahead and give this a little bit more of a concrete substance by actually taking some samples and watching these things happen. So I'm going to go into Excel and look at some data that I have here. So I have here 30 observations of a particular variable called hours. Now, this refers to the number of hours that were required to complete some task. Okay, and so we can look at some basic shape data about this. We see we have a lot of 20s, a lot of 15s, but also it goes down to as low as 3. So we can see that I've calculated the mean of this whole set here as being 12, and the standard deviation of hours is 7.4. Okay, so fairly large standard deviation, just from the fact that we have so many really small values in addition to so many really large ones. So what I want to do is to treat this as a population. Like, let's say this is the reality of the population, and I want to see what happens when we take samples and then look at the sampling distribution of the mean. Okay, so I'm going to go ahead and take 5 samples, 1, 2, 3, 4, 5. And before, in the last example, we were generating those. Your data analysis tool pack gives you a way to sample from a data set. So let's draw samples of size 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll look at the mean, and then we'll look at the mean of means and the standard deviation of means. Okay? So I'm going to go up to data analysis and sampling. And the input range is my population of values. Okay, so I've already got this selected here. It's cell B2 up to B31. Okay, and I'm going to draw 10 samples. Okay, that means randomly pick a value here, do it 10 times, and then put down what you find here. So I'm going to select an output range. Now here I can just select the top one and it'll fill in down. So I'll just do that and then click OK. All right, so it took a random sample, a random draw from these 30 values and wound up with these. And let me go ahead and calculate the mean here. So average of these, okay, and it was 15.3. Well, we'll color these so that we can keep them distinct here, okay. All right, 15.3. It looks like we overshot the population mean, so our sample here is showing a mean that is a little bit too large, okay. All right, so let's take a second sample then. Again, I'm gonna do the same thing where I go to data analysis, sampling from the same set. The only difference here is I'm going to set a different output range, and then just click this and click OK. All right, and I'm going to copy this because I want to. Whoops. I want to take the mean of all of these, so I'll copy from here. Okay. Now it looks like these aren't going to calculate because there aren't any observations there yet, but it looks like let me format that as normal. Okay, so it looks like this particular sample wound up with a mean that was actually too high, and this one was a little bit too low. So by virtue of sampling error that's inherent in this, we always wind up with a mean that's a little bit off. Okay, so I'm going to go ahead and quickly just generate 3 more samples, or draw 3 more random samples. So I'll just do data analysis, sampling. Now the only thing I have to change is the output range. I'll set it to there. Okay. All right. Now this one was way low. Okay. Sampling. Okay. Change the output again. Okay. And that one was high again. And final sample. Okay, and this one wound up being 10. Okay. Okay, so remember, let's double check. Our population mean was 12, and we kind of hovered around there with our samples. We were a bit high here, a bit low, pretty well low, a bit high, and a bit low. Okay, so the point here is that our samples are not exactly what our population mean is. So, what we conclude from this is that, we do have some sampling error here. I'm going to now take the mean of means here. So mean of means, or in the other slide, or in that slide, it was right here. So this is the mean of sample means. Let's see what this is. Mean of sample means. Mean of sample means. Okay, so average of these averages here. Okay, and it wound up being 12.2, which is pretty close to the true population mean. Okay, so this is a fact that is given to us by the central limit theorem. Okay, so we would expect to have a certain amount of error for individual samples, but over time those mean of means wind up being equal to the population mean. And in fact, if you take every single possible sample of size 10 and take those averages, it will wind up being exactly the population mean. Okay, so the other thing that the central limit theorem tells us is that the standard deviation of these means is going to be equal to this divided by the square root of the sample size. Okay, so our sample size was 10, so let's see if that is the case. So this will be our standard deviation of sample means. Okay, so standard deviation of all these things. Okay, 3.045. Okay, so we see the population standard deviation was this. So if we set this equal to that thing called the standard error of the mean, okay, which we set equal to population standard deviation divided by square root of the sample size, 10, okay, 2.3. Okay, now once again we see that these are not precisely on, but over time, if we were to draw more samples, our standard error of the mean and the standard deviation of those sample means would be the same. Okay, so what does this let us do? Okay, so the central limit theorem, in addition to letting us assume a normal distribution for our hypothesis tests, it also lets us quantify how much certainty we have with regard to our sample means. So again, remember that every sample was slightly different in its mean. And so if we want to say, okay, for this population, this is what the true mean is, we can't really just put a point estimate on it, because we have to quantify how certain we are that that is actually the population mean. And that certainty is going to be a function of how much variability there is across samples. So if from sample to sample we have an enormous difference in the calculated mean, then we are less certain about what the population mean is. But if we have a small amount of variation across samples, then we have more certainty about what the value of the actual population is. So this uncertainty in moving from the sample statistic to a statement about the population parameter is embodied in confidence intervals. So what we have with each of those sample means is a point estimate, just one single value that is the sample mean, okay? But because this is going to be a little bit off from the true population mean, we really need to give a confidence interval which tells us that how low can it be and how high can it be. So for example, if we say in that last example that we have let's say an average of 8, we say we had a sample mean of 8, but this could be, the true population mean could be everywhere from, let's say, 6.5 all the way up to 9.2, okay? But the idea is that this 8 is only our sample mean, and we can only be sure that the population mean is somewhere in here, okay? So the question is, how do we come up with these two endpoints here? Okay, and this comes from okay, let's go back to that sheet. Let's go back to this and think about let's say we've only drawn one sample, and it's this one. We've drawn one single sample, and so we wound up with 15.3. And so we have said, okay, well, we know that we have an estimate, a point estimate of 15.3, and we want to say, okay, it can be as low as something, and it could be as high as something else, okay? So, let's say we can use this standard error of the mean, right? Okay, so this wound up being, roughly our standard deviation, right? Standard deviation of our sample means. So let's just say, okay, well, let's say that this could be as low as this value minus 1 standard error of the mean, or as high as this value plus 1 standard error of the mean. So we'll do 1 standard error of the mean. Okay, so we'll say this is going to be equal to this minus, one of these, or as high as this plus one of these. Okay, so this is saying this is our confidence interval right here. Okay, our point estimate is that it's 15.3, but 1 standard error below that is 12.9, and 1 standard error above that is 17.65. And we see that this still doesn't contain the actual true mean. So, let's try again. Okay, we've got our point estimate here. All right, let's go down 2 standard errors. Okay, so let's say, okay, we're going to do, this is going to be equal to this minus 2 of these standard errors. Okay, and it could be as high as this plus 2 of these. Okay, so now we're saying, okay, well, our guess is centered at 15.3, but it could be as low as 10 and as high as 20. So this is 2 standard errors of the mean. Okay, so which of these should we use? Or should we use 3 standard errors, or 1.5 standard errors, or half a standard error? So if we're going to make a confidence interval, how wide that how many standard errors we should go up or down is going to depend on how certain we should be. We can see that if we go out 2 standard errors, that we have a range going all the way from 10 to 20. Now this would give us, we could be pretty certain that that's going to contain the true population mean. Okay, because that's a pretty wide range. That would be like me saying, I'm very confident that the average height is between 2 feet and 10 feet. Okay, I can be pretty sure that it's in there somewhere. So, but this only going out 1 standard error would be a low confidence. Okay, all right. So when we make a confidence interval, then how wide it is going to depend on how certain we want to be. Okay, so the way we do that is by multiplying it by, so here we have, so this is our point estimate, right? That was our sample mean. In our spreadsheet, it was that number there, plus minus, and then this is our standard error, right? So we used that before. So this is the standard error of the mean. And so what we're doing here with this is we're multiplying the standard error of the mean by something that corresponds to how confident we want to be. Okay, now we're going to get into these z scores, these these z scores that correspond to certain levels of probability. I go into those in another video, but something that's useful to know, I'm just going to give you some values. So if we're going to be using a normal distribution, which in this example we are, this number here, this z, if we want to be 95% confident, we use 1.96, and this is the usual case. usually we say that we're okay with a 5% chance of sampling error. We multiply it by 1.96. Now notice that's not quite what we did here. Here we were multiplying 2 times the standard error. Okay, so we don't need to multiply by 2 to be 95% sure. If we multiply by 1.96, we can be 95% sure. Okay, so if we only want to be 90% sure, then we multiply by 1.65. Now notice that what's going to happen is we're going to be multiplying by a smaller number. So it's going to be a narrower band. So let's say if we have a 95% interval, it's going to look like this. But if we only have 90% confident, it's going to be here. Okay, so if we the more certain we want to be, the wider we have to make those endpoints. Okay, and so a 99% confidence interval is 99% confidence level is going to correspond to multiplying by 2.5 standard errors. We don't really expect to ever do that. So the one that I want you to focus on is going to be the 95% confidence level and multiplying by 1.96. Okay, so this is how you construct a confidence interval. Okay, you start with your sample mean and you add and subtract some confidence adjustment number, usually 1.96, times that standard error of the mean. Okay, so let's take a look at an example and work it together. Okay, so let's say, again, here we have like an industrial engineering example. So if we have a sample of 11 circuits, okay, from a large normal population with a mean resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35 ohms. Okay, so population standard deviation is going to be 0.35. Okay, a sample of 11. Okay, so that means n is going to be equal to 11. Okay, and we have a mean resistance. Okay, so notice the sample mean is 2.2. Okay, so we have an X bar of 2.2. Okay, so we can, so this is going to be our point estimate. So our sample mean is 2.2. But the question is asking us determine 95% confidence interval for the true mean resistance of the population. Okay, so we can say, okay, we've produced 500, we've only sampled 11. We want to be able to say what is the mean for the whole production run from this 11. So we need to do a confidence interval. We can't just say 2.2. Okay, so this is going to be, so the confidence interval is going to be the sample mean plus minus, and then because it's 95, I said just as a guideline, just use 1.96 times the standard error of the mean. Okay, so it's going to be times this population standard deviation divided by square root of 11. Okay, so let's see, do we have a, okay, so we worked it out over here. Okay, so there's the sample mean, standard error of the mean, there's our multiplier. So what this is telling us is that even though our sample showed 2.2, we can be 95% confident that the mean of the entire set is somewhere between 1.99 and 2.4. Okay, so if we had a smaller population standard deviation or a larger sample, we would have had a narrower confidence interval. Okay, so just one word of practical advice here. When I ask for a confidence interval, you can express it like this. So it's going to be the lower bound less than or equal to and this is going to be the population parameter, less than or equal to the upper bound. But you can also express an interval, as you may know from other math classes, is just one, this can be, open or closed interval. It doesn't matter which. It's just writing the upper bound and the lower bound like this. Okay, so this is how you would express a confidence interval, these two ways. Just be sure that when you're stating a confidence interval that it actually does have two numbers. A confidence interval needs to be a range, so it does need to have two numbers. Okay, all right, so just a quick review of all the concepts. There's a lot that we covered there. Key takeaways is, a sampling distribution is a probability of a statistic across all possible samples from a population. Okay, on this spreadsheet, we drew, 5 samples, and so we got a sense of how this sample mean was distributed across all these different samples. Okay, so that's what a sampling distribution is. Okay, all possible samples. Okay, the standard error of the mean gives you a measure of the dispersion of the sample means around the population mean. Okay, so it's, this is the population, the variability in the population divided by the square root of the size of your sample. Okay, so this entire thing is the standard error. The larger your standard error, the more variability there is across your samples. Okay, and then finally, we went over what a confidence interval was, and we said that that gives you an upper and lower bound on the possible values of the parameter estimate. Okay, so to be more confident that the true population parameter is included in your interval, you have to make that wider. Okay, all right, so a lot to cover, but I hope that covers just about everything you'll need to know about sampling.